Hello everyone and welcome to the presentation. This is hopefully the first in a series of presentations I hope to give in regards to Docker and Kubernetes. This is going to start out with a bit of an introduction with Docker and containers and continue on to Kubernetes and a variety of other topics. So, this is all about the quest for efficiency. So we're going to start with a little bit of an introduction on containers, isolation and virtualization, and we're going to continue through Docker where it began and the OCI and CNCF. Then we're going to introduce a bit of the Docker concepts. That's a bit of a big bullet point there. And then finally we're going to end up with a little bit of Q&A. So, back in 1979 in Unix, a concept called chroot was introduced. Chroot was designed to be a utility to change essentially the location or the root of where an application or a process was executed. And this was designed as a way of isolating that process from other processes. Essentially, a process in a chroot did not have the ability of accessing the root and location processes of other applications that were running. So this process continued on, and eventually there was a concept termed the chroot jail. It was developed in 1991. It's kind of an continuation of that. And it was the idea that further that process would be isolated from other processes and did not have access to the resources that the other processes had, and vice versa. That concept has continued on, and in Linux it was developed the C groups and the namespaces concepts, 2006 for C groups. And C groups are the control groups. It's designed to isolate the various resources in the operating system, such as the storage and other resources like that, memory. Namespaces is designed to isolate things such as the process itself and what it can access, and the networking stack. So a namespace process has its own dedicated networking stack, which is completely isolated from the other processes. And so in 2005, Solaris introduced the Solaris containers, which was the first time the word containers was introduced. And this is designed to be chroot on steroids was the term that they used. That continued on with the LXC, or the Linux containers, in 2008, which was a further evolution of that concept. So as this continued on, virtualization, isolation, this all designed to be kind of a race for efficiency. As you can see the race at the bottom, this is basically what can we do the most with the least. And so with these various concepts, it continued to evolve. How can we further utilize the resources that we have available to us to do more? And basically the problem is that enterprises were purchasing these large, very powerful pieces of equipment, and they were discovering in their environment that they were not able to fully utilize them. They would have, for example, a mail server, which was very important to their enterprise, but that mail server did not utilize all of the resources available to it at all times, which meant that a very expensive server might be sitting idle 95 or even 99% of the time. So they developed various concepts to try and better utilize that process. Virtual private servers, for example, was one way of doing that. They had the ability of isolating various different web servers out into one physical box, but multiple virtual servers. So they had the ability of taking multiple loads, putting it on one machine to better utilize those resources. This concept continued on with the hypervisors. So with the Type 2 hypervisors, which is a bit of a retronym, this was the way that they were able to essentially start virtual machines. A Type 2 hypervisor is when you have a dedicated program on a running operating system that will virtualize a whole machine. And so this was kind of taking the containers, C groups, namespaces concept to a whole new level. They had the ability essentially to virtualize every aspect of a machine. So it was completely isolated from the rest of the host machine, and the background process, the hypervisor, would completely translate all communication to and from the virtual machine to the host. So they would do various things such as network bridging or complete isolation. They had the ability of dedicating a specific amount of CPU time or specific amounts of memory and taking virtual amounts of the hard drive and providing it to the VM. You were then able to run an entire operating system, Linux, Microsoft, Windows Server, any other type of operating system that was compatible with that hardware on another type of hardware. So running Linux on top of Windows, this was a pretty transcendental thing. And this very quickly became popular in the environment, and the virtualization revolution essentially started. Now, as this became popular, people started to realize, well, okay, I'm now running an operating system on top of another operating system. And the operating system it's running on may not be quite the most efficient. For example, do I really need Microsoft Solitaire installed on my hypervisor when all I really need to do is run the virtual machines? Well, no. So then the concept of the Type 1 hypervisor evolved. And so companies like VMware and Citrix developed their own hypervisor, which was essentially a very pared down operating system designed to do nothing but run the virtual machines. And so they gained efficiency in this. They took out a lot of the bloat in the operating system, and they had more resources available for running the VMs themselves. So this process will continue on with container hosts. So with VMs, we had a very great way of isolating a particular operating system from the rest of our environment. It was very well sandboxed, very secure, and honestly, it was very difficult for an application or an attack to break out of the VM and into the host system, which was great for security. Unfortunately, compared to containers, it was a very heavy operation. And so with the containers, people started realizing, well, okay, if we go back a little bit from the VM and we focus more on the container aspect, we can get further efficiencies with this process. As you can see from the graphic on the right-hand side here, there's a lot of bloat that comes from having guest operating systems on top of host operating systems with hypervisors in between. We're running all of the extra processes and utilities and things like that that are required for an OS on top of a program that runs the hypervisor, which is on top of another very bloated host OS. In some cases, a little bit less because we're using a Type 1 hypervisor, but nonetheless, it's a lot of extra stuff that has to be layered on top of other stuff. If we go back to containers, we can directly run a container on top of the container host within a regular operating system. We lose all of the extra bloat that comes from having to have the guest operating systems. And we can, in some cases, lose the hypervisor entirely as well. The advantage of the containers, especially in the Linux world, is that the container host itself is built into the operating system. So with the LXC and the other types of isolation, namespaces, secrets, these are concepts within the Linux kernel itself, which means that we can build a container which utilizes the processes within the host OS and doesn't need its own copy of them. So therefore, all we need to add on in a container are the binaries and libraries and the application itself in order to run what we need to run. This means a lot of efficiency. Typically, guest operating systems are going to run a couple gigabytes of memory, going to have maybe, in some cases, upwards of 20 gigabytes for the host storage, and a variety of other requirements. And so we get to drop all of that out of the process. So in this particular case, with a container host, we've created a great amount of efficiency. In fact, Docker goes so far as to estimate that you can have up to 40% optimization running the exact same workload directly on a host operating system with a container host, Docker, versus running that same type of operation with guest operating systems and a container host on top of the guest operating system. That's just with containers. Imagine if you were completely running the entire application and all of its dependencies directly within the guest operating system. So that amounts to a significant savings, which we'll go into a bit more in a second here. Now, CoreOS is also known as Container OS, is a product that was developed separately and eventually was bought out by Red Hat in 2017. It's designed to take this concept even further. The same way the Type 1 hypervisor saves space against the bloated guest OS or host OS running the VMs, the container OS can be optimized as well. And so you take your Windows Server and you remove all the bloat out of there and you pare it down to the bare essentials. In this particular case, CoreOS is Linux. But the same thing applies. You don't need all the GUI interfaces. You don't need all of the fun stuff that comes in a standard installation of Linux. So you pare it down and you get even further savings. Okay, so we started talking there about the guest operating system and the things that are needed to run. So if we try to run a container of one type on top of a host OS of another type, how does that work? So there is a little bit of a magic there in terms of the operating system required for the container. And so I've talked about the binaries and libraries that are required for a particular container to run its application. In some cases, the binaries and libraries are portions of an OS. And so we can have a container that runs essentially Ubuntu or Debian, but it's not really running it. All it really is are the libraries and various files that are required for those things to be done. Because remember, the host OS, especially Linux, is running all of the necessary virtualization that we need for the container. It's going to have all those kernel tie-ins directly utilizing the host OS. So there are just some translations that need to be done with those libraries and binaries that are provided, extra utilities, for example. And so with containers, there's further optimization to be done in that same regard. So you can see down there on the right-hand side, Server 2016 core, that container image by itself, no applications, no extra frills, was over 11 gigs. Now, that's a pretty massive size of a container when you start comparing it to the modern day Alpine Linux, which is only 5.8 megabytes. That's tiny. We're talking multiple orders of magnitude in savings there. So, as you can see with the server core, that's all of the extra operating system bloat being included. You compare it down, they started doing some optimization. Server 2019, less than half the size, 4.7 gigs. And then they got into Nano Server, which was their brand new thing. It started to spawn as its own operating system, and then they pared it away, and they eventually realized, well, this is really suited very well for containers, so they focus exclusively on containers for the Nano Server. And you can see now they're down to 250 megabytes for Nano Server 2019. 256 back up for 1903, because obviously they're adding a little bit of extra features as they go. But you can now actually run .NET applications inside of a Linux container. So for example, they have Ubuntu Bionic, Debian, Alpine, and those are even smaller than the Nano Server. We're down to 86.5 megabytes for running a .NET Alpine. So you can run a Microsoft .NET application inside of a Linux container that's only 86 megabytes. So, Docker itself, if we step back, a little bit of a joke here on the right-hand side. It works on my machine. Well, then we'll ship your machine. And that's how Docker was born. So this is a bit of a joke, but it also has a little kernel of truth to it. Part of the problem with applications and development is that on various machines, you're going to have various different dependencies and libraries and configurations, and it's not always going to work the same on everyone else's machine. So Docker took what LXC had built, which was essentially a way of packaging up all of the namespaces and C group concepts together, and they expanded it out even further. They said, what if we take all of this container virtualization and we start making discrete units? So if you take a particular set of all the binaries and libraries in an application and we package it all together in a ready-made product that can actually be distributed, that makes it a standardized unit of work. And so now they've consolidated a very standardized set of applications and requirements that can all be piled together. They took further on this concept and they introduced the concept of layers within the application. So you can have a base operating system and then layer the requirements on top of that. So you can start adding the .NET framework followed by the .NET application. And if you only make changes to a final layer, that means when you distribute the image, you only need to distribute the final layer, which also provides savings in terms of network transit. Now, Docker was not the only one in the game. In 2014, a competing product known as Rocket was released, and Rocket, later shorted to RKT, was eventually bought by the same group that distributes the Core OS, which is now owned by Red Hat. And Rocket was designed to do a lot of the same things that Docker did, but just in a different way, as it always is. Now, unfortunately, Docker and Rocket started competing with each other in a harsh way to try and obtain market share, and eventually the two companies came to the realization that this competition was not, unfortunately, healthy for their market. It was causing a rift between the container industry. And so eventually they came to a mutual conclusion that they needed to work together on an open standard, still being able to build their own respective products, but while also being able to agree and build up containers as a whole. So the Open Container Initiative was a sub-foundation of the Linux Foundation, which was designed to build that standard and share it so that other companies, in addition to Rocket and Docker, will also be able to build their foundations as well, and other applications would be able to leverage these. Now, this graphic here is a little bit misleading. Google was not involved in the founding of Rocket, but Google was involved in the founding of Kubernetes. And so the same way that OCI is responsible for developing the foundations of containers, the CNCF, Cloud Native Computing Foundation, was designed to build the foundations of containers as a whole and container orchestration. So what OCI is for Docker and Rocket, Kubernetes is for the Cloud Native Computing Foundation. Now these are all three groups part of the Linux Foundation. As you can see here, Docker started in 2014 working with the OCI to build their first commit of libcontainer, going all the way through the 1.0 of the OCI runtime format in 2017. Alright, so let's review a little bit about the Docker commands. So you're going to, of course, be able to run your image, and we'll do a little bit of a demonstration of that here in a second. There is also the concept of building your image. And so when you build an image, there's a declarative language that they use in a Docker file. You also have the ability of taking a running image and converting it, a running container, and converting it to an image. So you have, of course, the ability to save and load those images. And because containers have the ability of mounting volumes and extra file systems, you can also export and import that as a tar file. These are both the images and the file systems can be saved out as tarballs. And because we want to be able to share these discrete workloads, these containers, with other people, we have the ability to push and pull from a Docker repository, also known as a registry. Now the primary one is Docker Hub. This is the Docker one that's run. It's completely free to use and completely free to publish to, including creating your own private section of containers. Now, it is important to note that Docker Hub does require that your application be open source available for everyone. So if you do have requirements for your application to be maintained privately, you will need to, of course, create your own repository locally. Now, that's not to say that you can't utilize the public repository to pull in and build your own images. So, of course, we can also create our own containers. We can, without starting them, and then there are the commands to start, stop, and kill them as necessary. We can pause and unpause them in order to be able to delay execution of a particular process. And then there's a variety of tools that we can use to troubleshoot them. We can attach to a container that's been daemonized to run with it interactively. We can execute a process within a running container. We can use top, which is the ability to see the top running processes and the resources that they're utilizing. The CP tool, like in Linux, copies a file. You can either copy a file into or out of a container. There are some restrictions to that to note, by the way, with the hypervisor, the Hyper-V isolation. We'll get into that more later. And then we can utilize logs. It works with the Linux style of writing to standard out and standard error. And then we can use inspect, which also gives us a lot of the details regarding a running container. We can see the networking IP and various other resources. Finally, we can use the images command to see the available images locally on the system that have already been pulled. PS to see the containers that are either started, stopped, or running. We can use the RM tool, which will remove any container that's on the system, and RMI, which will remove any image on the system. So, how do we run a container? That's pretty simple, actually, and they give you a very great example on how to start with that. Of course, it's got to be hello world. So docker run hello-world is the very first command that they recommend you to run. And so you're going to see on the left-hand side here, all this does is it's going to execute a little bit of text to the screen, and it's going to terminate the container. On the right-hand side, we have a slightly different variant, which is the whale say container, and it's just going to give you this cute little graphic of a whale saying hello world. Now, the reason some of these demonstrations are important here, you're going to see at the bottom of both of these is that we have returned to the command prompt. We did not specify daemonization or interactive run, but by default you're going to get an interactive run. And so the fact that it has returned to terminal means that our container has terminated. And the reason that's important to note is because a container is defined by one primary process. You're going to be able to run more than one process at a time in a container, but there's always one primary process which dictates the life of the container. If that process stops, terminates in any way, that container is going to terminate. And so it's very important to note that you're not trying to deal with the life cycle of a container with various different processes. So there's always one major one, and then maybe some supporting processes. But primarily, you're going to be executing the one process. So further example here on the run command, there's a couple parameters here. These slashes, by the way, just denote a new line, a continuation of that line. So of course, Docker, the utility, run is the first command. -D is going to daemonize it. That means it's going to run that application in the background, non-interactively. N is specifying the name of the container. In this case, we've called it Redis. If you don't have to specify a name. If you don't specify a name, you're going to get two things. You're going to always get a GUID for your container, which you can reference at any time. But you're also going to get a randomly generated name, and they typically use a adjective and a noun. You're going to get something silly like jumping Einstein. The V command is designed to do volumes, essentially providing storage to the Docker container. Now, volumes come in two varieties. There is a standard Docker volume, which has the ability of providing storage to the container, which is non-host oriented. It's essentially going to create a file somewhere in the file system that acts the same way that a virtual hard drive does for a VM. It's going to give storage to that container, but it's not tied to the operating system of the host directly. The other type, of course, is a direct host map. And you're going to be able to map either a directory or a particular file into the file system. You can see here in this particular case, we've actually got a hybrid. We are on the left-hand side, which is the host, mapping a config file on a Windows file system on the right-hand side to a Linux location inside of the container. So this would be if we're running a Linux container on top of a Windows operating system. And there are some caveats that are important to note here. You do have to pass permissions. There are some dangers, of course, with being able to have your containers access resources on the host system. And if you're running secure Linux, you will need to pass other various parameters, such as the :Z, to give it permissions to read and write. The next line, -P, is mapping a port. So on the left-hand side always, and I like to think of it as the left-hand side is a little closer to the shell. That's how I remember that that's going to be the host side, is mapping on the right-hand side to the container. So we've mapped 6379 inside of the container to port 6379 on the host, which means that any activity that occurs on the network stack on 6379 in the container is going to be visible or accessible from the host, which means we could at any time now go ahead and access Redis by hitting port 6379 directly on the host. If you don't map this port, that port's not going to be available to the host operating system. You're not going to be able to see that because remember, the container has its own network stack and its own IP address. And by default, that's isolated, and this is a deliberate design. The next parameter, restart, sets the restart policy, and you can use an always policy, so that this means essentially that if for whatever reason this container terminated abnormally, it would restart itself. If the if the container host process, Docker itself, for example, terminated, if it came back, it would restart the container. Or if the entire host OS itself restarted, this container would restart once the Docker daemon restarted again. You can specify other policies such as never or if running, which basically means that if you stopped it, it would not start itself again. The final command there is indicating the image that you want to run. By default, you're going to access images from the Docker host. So if you don't specify the repository that you're trying to use, it's going to try and pull it from Docker Hub. In this particular case, we're pulling the Redis image, and after the colon there, this is the tag. So we're using the tag 5.05-alpine because we want to pull version 505 of Redis, and we're using the Alpine baseline. So many of the Linux containers, they frequently start their baselines with Debian, but they also usually provide an Alpine version. And this is important to note because the Alpine version is dramatically smaller, but there may be some instances in which it doesn't provide enough utilities for you to be able to do what you need to do because Alpine strips out a lot of utilities. So we talked earlier about the Docker files and the declarative language. So they use what they call declarative state language. And what this is going to do is try to set a particular state within the container. So with this Docker file, we have two different sections here, as you can see, and we're going to be setting up a builder. And in the builder container, we're using the from command to pull in this Microsoft.NET SDK Jessie container. We're going to copy files from the host at myapp to the container at myapp, and then we're going to run a single command here. And this is specifically done with multi-line commands so that this is treated as a single layer. If you were to put each of these .NET commands on its own run line, it would end up as different layers, and that can increase the size of your image unnecessarily. So in this particular case, we're going to restore the myapp, build it, and then publish it. Once we're done with building it, we can actually use a new container now for the final build. We're going to take the runtime container this time, and we're going to do a copy command. And this from 0 indicates container 0, so this is ordered from 0 up. This is 0 and this is 1. We're going to take the myapp pubdir that's been built up here, and we're going to copy it to myapp in this brand new container. We're going to set an environment variable here, this ASP.NET Core URLs, and we're going to specify it's that port 80. And then we're going to set an entry point. And so the entry point, remember I talked earlier about the primary process. So in this particular case, what we're setting the primary process is to .NET. And then we're giving it a parameter, this myapp DLL. The final line here, expose 80, is, remember I told you that the networking stack is isolated. This is going to expose port 80 inside of the Docker host. This means that other containers will now be able to access port 80. Now, keeping in mind, again, if you do not use the port mapping command with a container run, the host is not going to be able to see that. But the other containers will be able to access the network IP of this particular container at port 80 to see that information. So you got to remember to expose those ports if you want your containers to be able to communicate with each other. Okay, and if we move on here, we're wondering a little bit about these containers. Remember, it's a public repository. We kind of have to do a little bit of implicit trust as to whether these things are going to be safe, but you do have a few utilities available to you and ways of determining whether or not these containers are safe. One of the options is the Docker history command. And so with each of the layers that is accumulated within a particular image, you're going to be able to see that history. And so on the left-hand side there, you can see the image GUID, when it was created, what the command was, and how much space it added to the overall container image. And so you can see at the very bottom there, they added a file, then they set the CMD, which is the default shell of the container. They set the working directory, which is basically the default location where we're going to run applications, and so on and so on. And so you get a little bit of an idea of what's been done with this container. And so now you know essentially what's gone into this. Now there's a little bit of a caveat with this. This is all done based on the Docker files. Remember I said earlier, you have the ability of building an image by essentially starting a container image and then saving it in as a new image. And so you're not going to get the whole list of those commands with this Docker history process. But you do have other commands available to you. You can start up a container, for example, in a test machine, and you can do some poking around. You can see what's inside of it by using ls and other utilities. You also have the ability of stripping all the layers apart and checking out all the files directly by scanning it, because remember, these are all just tarballs after all. There are other ways of telling whether something is good or not. There are, for example, websites that are providing their own registries for containers, and they will provide their own security scanning processes. So they will actually take and see, all right, this particular image was built with this particular kind of operating system baseline, and determine all the vulnerabilities. And they're actually going to scan all that and apply all the CVEs and show you the levels of criticality and so forth like that. So containers are designed to be stateless. And what that means is they start, they perform a particular task, and then they terminate. They're not designed to maintain information between themselves. Now, of course, the exception of that is that you've mounted storage or you've provided information to them as they're executing. But the container itself is designed to be stateless. So if you have a particular issue with a container, rather than like a virtual machine or a physical machine where you have to go and try and fix it or completely reinstall it, in this particular case, you're just going to kill the container and you're going to start again because it's gotten some kind of issue. Now, of course, if you have issues with the data, that's a different problem entirely. But this is alluding to the pets and cattle concept, which is very popular with containers. And so rather than spending your time very carefully maintaining your pets, because if Fifi died, you were going to be very sad. But with the cattle, cow 1397 dies. Unfortunately, that's a write-off, but you're not nearly as sad. It makes a lot of sense in terms of efficiency because rather than spending a lot of time trying to fix a very sick container, you're simply going to terminate that container and start over again. And so that can be a significant cost savings. So, as I mentioned earlier, there are also several different kinds of Docker isolation types. So the very first one and the primary one is going to be the process isolation type, and that's based around the original namespace cgroup concept. This is basically you are running a process on the system. It's simply got a couple bits of isolation wrapped around it. And so they talk about, oh, you can start a container up in 50 milliseconds. Well, all that's saying basically is you can start a process in 50 milliseconds. That's no different than it was before. So this does not have all of the virtualization that a VM does. It does not have all of the safeguards that a VM does. It has the namespace and cgroup stuff, which is very powerful, but it's not to the same level of isolation. So that is important to note in terms of security. Don't try to download a virus from the internet, put a container, and expect it to be 100% completely secure. It might be, but it might not be. So there are, of course, process isolation types for Linux and for Windows. And so Linux has the native namespaces and cgroups concept built into the Linux kernel. That's not quite the case with Windows, although they are working towards that direction. So they have the concept of the HCS shim, which is essentially just a shim process designed to handle some of that virtualization. And so sometimes you'll find, working with containers, you'll see issues with the HCS shim, but they're getting better all the time with this. Linux containers are old. They're very well known. They've been very well debugged. Windows is much later to the game, so they're still catching up in a lot of ways. The next type is the Docker Hyper-V isolation. And so, of course, this relates to Windows. Containers again. You are now isolating the container by using Hyper-V. And so essentially you're spinning up kind of a pseudo VM. You're isolating a little bit of the Windows processes in the same kind of way the HCS shim does, but with a little bit more of a VM attached to it. It's a little bit complicated, but suffice to say that there are important distinctions. With a process, you're able to utilize all the things that a process can. Now, there are some safeguards to prevent you from being able to use all the RAM and CPU cores and things like that with the process isolation, but in general, you basically can. If a particular process wants to use 40 gigs and you haven't set a limit, it's going to be able to take all that RAM. With the Hyper-V, there are some defaults. Hyper-V will default to 1 gig of RAM, which is important to note if you try to run something like Microsoft SQL Server in a container, which is very possible. But it does not like running with 1 gig. You do need to increase that with the -M parameter. There are also limits on the amount of storage that can be directly accessed with Hyper-V. That is by default 20 gigabytes, which can also be increased by parameters in the daemon configuration. Docker lcow, which is the Linux container on Windows, is a way of running the Linux container on Windows. Surprise, surprise. What this is doing is, again, a bit of a Hyper-V. You're now taking essentially a Linux Hyper-V VM and utilizing that to provide the core OS to run the way you would a regular Linux container. So now there's a little bit of a VM involved. You're getting a little bit less efficient, but you are getting a little bit more secure because now you have the virtualization of a VM protecting you a little bit more. But again, this is a little bit different than running a process directly on Linux. You now have additional limits. So you have to set the RAM that's available to that VM. You have to set the hard drive and so forth like that. And so there are considerations in that regard. But it is a very quick and easy way of being able to run Linux containers on a Windows system. So if you're doing some testing locally on your Windows box, this works really well. Now, there is a new feature coming out for Windows, which is the Windows subsystem for Linux. And they actually have Windows subsystem for Linux right now, which is available. But version 2 is coming out. And this is designed to, this is with Windows 10 Insider Preview build 18932 or later. So even with the current version of Windows 1903, you can't do it yet. You do have to be an Insider Preview build. But this is a very fancy way of running the containers. because now what you're utilizing is a brand new Microsoft feature to run essentially Linux within the Windows OS without having a huge heavy VM. So now you're going to be able to much more efficiently run your Linux containers on Windows without all the bloat of a huge VM. And so, of course, this is the future. But you can see in the top left hand here, they have the ability of running Ubuntu or SUSE or Fedora directly within a shell on Windows. And basically, you're doing a small little install of Windows using this Windows subsystem feature. Okay, and so I mentioned earlier there are different types of running Docker. So there is the original Docker toolbox concept, and this kind of continues today, but it's mostly deprecated. Um, the Docker toolbox was designed as a way of getting all of the Docker stuff from Linux to other operating systems, Mac and Windows. And you can see over here this cute little graphic of the toolbox. They have the Docker machine, they have the actual Docker engine, Swarm is available, among other features. And so this was a little more heavy on the virtualization. It relied a lot more on the VMs that the Hyper-V and the LCOW did. So there was actually a requirement for VirtualBox or for Hyper-V to be running in order to be able to get Docker Toolbox to work, which meant you couldn't directly run those containers, even Windows ones, without those features. Docker Desktop is the new hotness. It does require Windows 10 1809 or higher or Server 2016 to run, but it does directly now let you run the Windows containers with that HCS shim. You can actually run with Windows 10 1809 plus the process isolation for Windows applications on a Windows 10 system. You didn't used to be able to do that due to licensing from Microsoft. Essentially, they said, well, you're kind of running a Windows Server OS process on a client. That's not really what we intended you to do. But eventually they relented. And so now you actually have the ability of doing process isolation directly on a Windows 10 system. If you don't specify process isolation, however, it's important to note that with Docker Desktop that you do default to the Hyper-V isolation. Docker Engine is, of course, the enterprise version. There is a community supported edition, but there's also the paid enterprise edition. This is the stripped down version. It's purely the engine. It's designed to be small, efficient, quick to install, and so on and so on. And so this is supported with Server 2016 Plus. Although it is important to note that there are significant advantages to running with 2019 or even going to the semi-annual channel versions of Server. You get a lot more efficiency and so forth and so on. Because as again, Windows is late to the game, they're still developing a lot of their features and capabilities to the Docker system. Honorable mentions to this process as well. These are not daemon types, but they're important to note. Docker Compose is a way of building up containers or even groups of containers using a YAML file. It's a bit like the Docker file, except for it's designed to spin up the containers as opposed to building the container image. And so you can declare things like networks and volumes, processes, give them names, have them ability to communicate with each other. You can declare requirements, so don't spin up this application until this other container which contains the database starts. So Docker Compose is a very easy way of grouping all of your applications together and having them all start together in the right way. Docker Swarm is a container orchestration feature within Docker itself. It is essentially a simplified version of what Kubernetes is. It's designed to give you the service discovery and scale out features of Kubernetes in a more localized fashion. So that's useful as well. All right, so that basically concludes the presentation here. So there's a couple of resources I provided up here for you. I recommend this top one in particular. This Get Started Training actually gives you some labs and videos that will help you get familiarized with Docker itself. You can actually run some containers on their lab without having to even install the process. Of course, the official documentation is very useful. It's going to give you all the commands and all the details regarding the commands. As you continue down your road, there is a very useful website, the Kubernetes Academy. This is a brand new website developed by VMware because VMware is now very heavily invested in the container architecture. They've kind of realized that this is the natural evolution for virtualization, so of course they want a piece of the pie. And then this training website, oh sorry, I got this confused. This training website is the one with the labs, and then this up here is the Docker documentation on how to get started. A little bit of information about Druid here gives you a little bit of the history as well. And so from here, if you would like to provide any questions, I would be happy to give you any answers.